Good evening, and welcome tonight. You do not need to solve anything. You do not need to hold every idea in place, or carry every detail to the end. You do not need to be brilliant, alert, or sharp. You only need to listen in the soft way people listen to rain on a window, or to a distant train passing through the dark, or to the quiet hum of a room that has already decided to rest. The world you know during the day is made of dependable things. Floors stay beneath your feet. Tables remain where they are left. Light falls across a wall and seems to travel exactly where it should. In daylight, the universe appears to keep its promises. It seems solid, tidy, and politely obedient, but beneath that familiar surface, under wood and stone and breath and skin, there is another layer of reality. It is smaller than sight, smaller than dust, smaller than almost any picture the waking mind can comfortably hold. And in that hidden layer, the rules are softer, stranger, and more dreamlike than the rules that guide ordinary life. There, something can spread like a wave and arrive like a point. There, emptiness is not fully empty. There, distance does not always mean separation in the way we expect. There, certainty loosens its grip. There, reality does not always seem fully decided until it is gently asked to be. And yet, for all its mystery, this hidden world is not hostile. It is not a place of alarm. It is only deeper than habit. It is only quieter than explanation. It is the secret underside of the same universe that carries the moon, the sea, the turning of leaves, the warmth of a blanket. So tonight, as your thoughts begin to soften and your attention becomes less like a bright lamp and more like candlelight, we will drift downward into that unseen realm. Not quickly, not forcefully. We will go slowly, as if descending a long staircase in a house where everyone else is already asleep. And if some part of this journey slips past understanding, that is perfectly fine. In fact, that may be the best way to hear it. Quantum physics does not always reward the tight grip of the mind. Sometimes it is kinder when received like music. Sometimes it settles more naturally when it is allowed to remain a little unfinished, a little blurry at the edges, a little like a dream remembered only in pieces by morning. So let the day recede, let the body grow heavier, let the room become larger and quieter, and let us begin, not with a formula, but with a feeling. Imagine the world shrinking, not the way a toy version of the world shrinks, keeping all its familiar proportions, but a deeper kind of shrinking, where the ordinary rules themselves begin to loosen. Imagine moving inward through fabric, through skin, through cells, through molecules, past the neat chemistry of daily life, and farther down into a hidden architecture where matter is no longer made of little solid pebbles, but of patterns, possibilities, whispers of location and energy. At those tiny scales, the universe does not behave like a collection of miniature marbles. It behaves like something softer and harder to pin down. Crisp outlines we trust in daily life begin to blur. Motion stops looking like a simple path from one place to another. Events stop feeling like little mechanical pushes and pulls. Instead, reality becomes hazy, probabilistic, alive with things that are not impossible, only unlikely. In the daytime world, it is comforting to believe that if we look closely enough, measure carefully enough, and think clearly enough, everything can be known exactly. But in the quantum world, exactness begins to slip through the fingers. There is knowledge, yes, and there is stunning precision, but there is also a built-in softness, as though the universe keeps one corner of itself folded away. And perhaps that is part of why this hidden realm feels so soothing at night. It reminds us that not everything must be fixed and sharp and settled. Not everything must be held in perfect clarity. The foundations of the world themselves are more fluid than they seem. So as we drift farther in, let that be our first comfort. Beneath the rigid appearance of things, reality is already gentler than it looks. And you, listening now, do not need to understand everything. You only need to float. You do not need to remember every term or distinguish every particle from every field. You do not need to assemble the whole structure in your mind. This is not an exam. It is not a lecture hall. It is not a race toward a conclusion. Think of this instead as a long, slow walk through a museum after closing time, where the lights are low and the signs are written in a language you do not fully read, but the rooms are beautiful anyway. You move from one chamber to the next, carrying not mastery, but mood. You leave not with a list of answers, but with a softened sense that the world is wider than it felt before. That is enough, perhaps more than enough. The mind often believes it must grip a thought to keep it, but sleep asks the opposite. Sleep asks us to let thoughts arrive and depart without argument. It asks us to trust that not all meaning must be consciously preserved. Quantum ideas, with all their mist and strangeness, fit beautifully into that gentler rhythm. They can pass through the mind like moonlight through thin curtains, leaving a faint glow without demanding total attention. So if you notice yourself drifting, that is not a failure. If your thoughts blur or float or briefly leave the words behind, that is not a mistake. That is the correct weather for this journey. Let the harder edges of thought dissolve. Let the need to fully follow begin to soften. The universe has been carrying its mysteries for a very long time. It can carry them a little longer without your help tonight. Now, with that permission in place, we can step toward the first doorway. The strange truth is that the smallest scales of existence are not governed by the same style of certainty that rules daily experience. The deeper we go, the less the world resembles a clock, and the more it resembles a piece of music still being played. One of the earliest clues came from energy itself. For a long time, people imagined energy as something smooth and continuous, like water pouring from a jug. Light seemed to stream, heat seemed to flow. Everything suggested a graceful continuity, unbroken and endlessly divisible. But nature, in its quieter depths, had chosen a different style. Energy, it turns out, often comes in tiny packets, little measured portions, small indivisible steps, not a smooth, endless stream, but something closer to a delicate staircase. This was one of the first great surprises of quantum theory. Under the right conditions, energy does not arrive in any amount whatsoever. It arrives in set amounts, little parcels, as though the universe prefers coins to liquid, notes to blur, droplets to fog. That smallest packet is called a quantum, and the word is gentle once you sit with it. A quantum is simply the smallest allowed exchange, the smallest step by which a system may gain or lose energy. A tiny unit of change, a minimal pulse in the hidden bookkeeping of the world. This may seem abstract, but it quietly shapes almost everything. Why hot objects glow the way they do. Why atoms accept only particular amounts of energy. Why light can be emitted in sharply defined colors rather than every possible shade. The world, at its smallest scales, does not merely slide. Often, it clicks. There is something oddly restful in that. A universe made not only of smooth continuities, but of tiny, careful measures, as though reality itself were breathing in counted beats. And once that first door opened, once scientists realized that nature preferred these hidden steps, more doors began to appear. each one stranger than the last, each one opening not onto chaos, but onto a deeper kind of order, one less obvious and more dreamlike than the order of tables and clocks and roads. One of the most famous of these doors concerns light. Light is so familiar that it almost feels too ordinary to surprise us. It rests on morning floors. It slips across water. It warms skin. It paints shadows against walls. It seems among the least mysterious things we know. And yet light is one of the great shapeshifters of reality. Under some conditions, it behaves like a wave. It spreads, overlaps, interferes with itself, and forms rippling patterns that look exactly like the patterns made by water. If light passes through narrow openings, it can create bands of brightness and darkness, the soft signature of waves combining and cancelling. But under other conditions, that same light behaves as though it arrives in individual little impacts, one point at a time, like tiny messengers striking a surface. Wave and particle, spread and point, flow and hit. The mind wants to choose one. It wants to tidy the matter, to say that light is secretly this or secretly that. But the quantum world does not always honor that wish. It asks us to hold both aspects at once, not because nature is confused, but because our everyday categories are too small for what light actually is. And strangeness does not end with light. Matter itself behaves this way too. Electrons, atoms, even larger collections, under the right circumstances, can reveal the same dual character. They can move in ways that produce wave-like patterns, and yet be detected as particular arrivals. This is one of the reasons the quantum realm feels so much like a dream. Things are not always only one kind of thing. They do not always fit neatly into the boxes we prepare for them. They spread, they gather, they remain indefinite, and then, at the moment of contact, they appear. It is as if the world at that scale prefers suggestion to declaration, as if it would rather hum than point, and perhaps that is why it belongs so well to the hour before sleep. There is another famous doorway, even stranger, and it asks a question that feels almost philosophical. What does it mean to observe something? In ordinary life, observation feels passive. You look at a chair. The chair does not care. You notice a cloud. The cloud goes on being a cloud. In the larger world, seeing seems separate from changing. But in the quantum world, measurement is not so innocent. To observe something tiny, you must interact with it. You must use light or another physical process to ask the question. And in asking, you disturb. The act of measurement is not merely peeking through a window. It is more like brushing the surface of a still pond and then trying to say what the water was doing before your finger touched it. In some experiments, particles create wave-like interference patterns when no attempt is made to track which path they took. But when a measuring device is arranged so that their path becomes knowable, those patterns disappear. The system behaves differently under observation. This can sound, in casual retellings, as though human attention magically changes reality. But the deeper idea is subtler and perhaps lovelier. Measurement is physical. It is contact. It is involvement at tiny scales. There is no perfectly detached glance. To ask is to touch, and so the universe at that level seems to preserve a special kind of privacy. It does not reveal everything without consequence. It does not allow itself to be fully known without becoming, in some way, different in the process. There's something gentle and ancient in that too, a reminder that some truths cannot be approached without altering them. A reminder that closeness changes what it touches. A reminder, perhaps, that reality itself is relational. Not a set of inert objects waiting under harsh light, but a living pattern whose details depend, at least in part, on the manner of our encounter. As the night grows deeper, This idea can be strangely comforting. Nothing is fully isolated. Nothing is observed from nowhere. Every act of knowing belongs to the world it knows. And if that sounds too large, let it fade into a softer thought. Even the smallest things do not like to be stared at too hard. The next truth is one of the quiet pillars of the quantum world, and it concerns uncertainty. In classical physics, the dream was beautiful and severe. If you knew enough about a system, if you measured it precisely enough, then in principle you could know exactly where it was, how fast it was moving, and where it would go next. The universe would be a vast machine, and prediction would be the art of reading its gears. But at the quantum scale, that dream begins to blur. There are pairs of properties that cannot both be known with perfect precision at the same time. The more tightly one is pinned down, the more the other slips away. Position and momentum form the most famous pair. If you know exactly where a particle is, you lose precision about how it is moving. If you know its motion with great precision, its location becomes less definite. This is not merely a flaw in our tools. It is not a temporary inconvenience awaiting better machinery. It is woven into the way the world is built. The universe, at its deepest levels, does not always possess the crisp simultaneous facts we wish to assign to it. That can sound unsettling when heard in bright daylight, but at night, it can feel like permission. Permission for things to be partially known. Permission for reality itself to be more like a field of possibilities than a ledger of exact entries. And perhaps permission for us, too, to live without closing every open question before sleep. This uncertainty does not mean disorder. It does not mean anything goes. Quantum mechanics is astonishingly precise in what it predicts. But it predicts probabilities, not certainties. It tells us what may happen and how likely each outcome is. It does not always tell us what must happen in advance. So the universe, underneath its calm appearance, is not a rigid script. It is more like a score with room for variation, a carefully structured openness, a lawful softness. And in that softness, there is an odd beauty. A particle may not have a single definite position before measurement in the way we casually imagine. Instead, it is described by a spread of possibilities, a wave of potential location. That wave does not say where the particle definitely is. It says where it might be found, and with what likelihood. And so we arrive at one of the most haunting ideas in all of physics. Superposition. A word that means, in the gentlest terms, that a quantum system can exist in more than one possible state at once. Not because it is confused, not because we are ignorant, but because the underlying description of the system genuinely includes multiple possibilities together. An electron can be in a blend of different states. A photon can travel along overlapping paths. A quantum bit in a computer can hold more than the simple certainty of 0 or 1. Before measurement, the world at that scale is not always one thing or another. Sometimes it is a structured mixture of both. This is difficult for the waking mind because daily life trains us to think in single outcomes. Cup is on the table or not on the table. The door is open or closed. But quantum reality, before it is forced into a definite result, can occupy a more fluid mode of being. A cloud before rain, a chord before resolution, a story before its ending is chosen. Superposition does not mean that anything can happen in any way at all. It is not chaos. It is pattern with multiple branches held together. A delicate balance of possibilities. And when this system is left undisturbed, those possibilities can interfere with one another, adding and subtracting like overlapping ripples in a pond. That interference is one of the keys to the power of quantum systems. It is also one of the reasons they feel so unearthly. The world at that scale does not merely wait to be discovered. It evolves through possibilities, and eventually something happens. A measurement, an interaction, a definite result. One outcome appears. The many become one. How that transition occurs is among the deepest puzzles in all of science. The mathematics of quantum theory tells us how the wave of possibilities changes over time. It does so smoothly and beautifully. But the moment a single outcome is obtained, we describe the wave as collapsing into one result, a sudden narrowing from many possibilities to one experienced fact. Yet, what is this collapse, really? Is it a true physical event? Is it a shift in knowledge? Is it merely the appearance of collapse within a much larger reality? No single answer has won the night entirely. And so, near the center of quantum theory, there remains a soft chamber of uncertainty, a place where even experts still speak with different voices. Some say the wave function truly reduces. Some say every possibility continues somewhere, and we merely find ourselves in one branch. Some say the question itself may be framed too narrowly. Some say the environment surrounding a system quietly erases the delicate overlap, making one outcome effectively real for practical life. But for tonight, we do not need to choose. We only need to appreciate the mood of the thing. Reality, at its smallest scales, does not always begin as a single path. Sometimes it begins as a murmuring field of could be, and only later, when touched, does it harden into was. There's a famous image used to express this strangeness, and though it was invented partly to show how absurd quantum thinking can feel, when extended to everyday objects, it has lingered in culture like a half-remembered fable. Imagine a sealed box. Inside is a cat. Also inside is a mechanism connected to a tiny quantum event, perhaps the decay of a single atom. If that event occurs, the mechanism is triggered. If it does not occur, the mechanism remains still. Before the box is opened, quantum theory suggests that the triggering event exists in a superposition of possibilities. And if the whole arrangement is carried upward into that quantum logic, then the cat seems suspended in a bizarre state, not simply alive or dead in the ordinary way we would like to assign, but linked to a still undecided event. The point of the story is not that cats truly hover in such conditions in everyday life. The point is the eerie mismatch between the quantum world and the scale of human experience. The thought experiment asks us to feel, almost physically, how strange superposition becomes when we try to drag it into the visible room. And yet even here, in this unsettling little image, there is something useful for sleep. The cat in the box is not really a problem to solve tonight. It is a lantern illuminating a boundary. It shows us that the universe has layers, and that the rules of one layer do not always arrive intact in another. Somewhere between atom and animal, possibility narrows. Somewhere between hidden mathematics and familiar life, the world settles into the definite. How exactly? Still, a mystery. But the mystery itself has become part of the beauty. And now, as we drift onward, we come to one of the most astonishing connections in the quantum landscape. Entanglement. It is a word that sounds like silk thread, and in a way that is fitting. For entanglement refers to a relationship between quantum systems so deep that they can no longer be fully described on their own. Their properties become linked, their identities, in a real sense, become shared. If two particles interact in the right way, they can enter a combined state. Afterward, even if they move far apart, the full description belongs not to each one separately, but to the pair together. Measure one, and the possible results for the other are immediately constrained. This does not mean a little signal has raced through space in the ordinary sense. It means the two systems were never fully separate to begin with. The correlation was built into the joint state from the moment of entanglement. Still, to the everyday mind, it feels almost magical. Two particles created together may carry a bond so deep that distance does not restore independence. Miles, planets, even the width of space do not fully sever what quantum theory has joined. There is something tender in that image, a shared condition stretched across darkness, a single pattern appearing in two places, a reminder that separation may not always mean what it seems to mean. This idea troubled many people, including one of the greatest physicists in history, Albert Einstein, who helped build some of the very foundations of modern physics, was deeply uneasy with entanglement. He did not like the thought that the world might contain these non-classical correlations. He hoped there might be hidden details, deeper variables, some unseen layer restoring a more familiar kind of reality. Along with colleagues, he proposed arguments designed to show that quantum theory might be incomplete. Surely, he felt, there must be more behind the curtain. Surely the universe would not settle for such eerie connectedness. But the curtain did not open in the way he hoped. Later work, especially the profound insight known as Bell's theorem, showed that any theory based on ordinary local hidden variables would impose limits on the kinds of correlations entangled particles could display. Quantum mechanics predicted stronger correlations and experiment over and over, sided with quantum mechanics. This is one of those moments in science where the universe quietly refuses to become simpler merely because we would prefer it. The world does not always return to common sense. Sometimes common sense must become larger. And perhaps when heard close to sleep, this is not a threat, but a comfort. Perhaps it is soothing to know that reality exceeds our habits of thought, that the world is not exhausted by what feels intuitive, that there are forms of connection deeper than daylight logic. Entanglement is not just a philosophical oddity. It is real enough to be used. It lies at the heart of quantum communication, quantum cryptography, and many proposals for quantum networks. But before it becomes technology, before it becomes engineering, it remains something more basic and more lyrical. It is evidence that the universe can hold relations more intimate than simple distance, that what happens in one place may belong, in part, to a whole that extends elsewhere, that beneath the lonely appearance of things, the world may be stitched together more tightly than it lets on. From here, another strange possibility opens. Quantum teleportation. The phrase sounds theatrical, like a door to science fiction, but the actual process is quieter and more subtle than popular imagination suggests. It does not move a physical object bodily from one place to another. It does not dissolve a person into light and reassemble them elsewhere. Instead, it transfers the state of one quantum system onto another, using entanglement and a carefully chosen measurement. One particle is prepared in a state we wish to transmit. Another pair of particles is already entangled, one near the sender and one near the receiver. Through a special joint interaction, the original state is destroyed in one location and reconstructed in the other. Once the necessary classical information is also sent. Nothing large moves through space in a flash, and yet something important does move. The identity of the state, the precise quantum pattern, do not. There is something oddly poetic in this, a kind of transfer without travel, a continuity of form without a journey through the ordinary middle. The state does not stroll across space. It is here, and then there, like a melody played by one instrument and then taken up by another across the room. Quantum teleportation is already a real laboratory achievement. It has been demonstrated with photons and other systems over increasing distances. It forms part of the dream of a future quantum internet, where fragile states may be distributed and preserved across networks more subtle than our current ones. But tonight, beyond the engineering, let it remain what it first feels like, a whisper of identity leaping the gap, a pattern carried not by bulk, but by relation, a reminder that information itself may be one of the deepest currents in the universe. And from there, the mind can drift into an even wider speculation, one that has become increasingly intriguing in modern theoretical physics. What if space itself, the very fabric in which things seem to sit, is not fundamental in the way we once imagined? What if geometry, distance, even the smooth stage on which the universe appears to act, might emerge from deeper quantum connections? This is still a frontier idea, incomplete and debated, but deeply beautiful. In some theoretical frameworks, entanglement does not merely occur within space. It may help give rise to space. The links between quantum systems may be related to the structure of geometry itself. Pull apart the pattern of entanglement enough, and the space-time picture might begin to fray. It is a startling thought that what we call near and far, connected and separate, might arise from a hidden web of informational relationships beneath ordinary reality. That the room around you, the city beyond it, the planet, the silent reaches between stars, may all rest upon a deeper kind of weaving. And if that is true, then the universe is not a pile of isolated things, scattered through an empty box. It is a single fabric, quietly knotted at this point in our journey. It is good to rest. The mind has traveled through packets of energy, uncertain motions, overlapping states, mysterious collapse, impossible cats, linked particles, teleporting identities, and the possibility that space itself grows out of invisible bonds. This is enough strangeness for one stretch of night, so let us step back for a moment into calm. Imagine not the equations, but the silence beneath them. Imagine the room again, the stillness of air, the patient dark around the furniture, the soft weight of the bed, the slow tide of your own breathing. All of these quantum mysteries, however wild they sound, live beneath the quiet surface of the same ordinary night. They are not elsewhere. They are within the wood of the floor, the fibers of the blanket, the warm chemistry of your body, the tiny electrical signals moving through the sleeping brain. The strange world does not replace the familiar one. It supports it. It hums beneath it, and that can be very soothing. The world is not broken because it is mysterious. It is simply deeper than habit. Now, when you are ready, we can descend again, this time toward the particles and fields that populate the hidden layer more directly. Consider the electron. It is one of the most important ingredients in the visible world. It helps bind atoms into molecules. It flows through wires. It shapes chemistry, biology, electricity, and much of the practical world around us. And yet, the electron, so essential and so familiar in its effects, remains profoundly hard to picture. When physicists probe it, the electron behaves as though it has no internal structure, no little gears or smaller pieces waiting inside. It appears point-like, fundamental, not obviously made of anything simpler. And yet it also refuses to behave like a tiny grain sitting in one exact place until pushed. In an atom, the electron is described by a spread of possibilities, a cloud of probability around the nucleus. This cloud is not a little dust cloud made of material substance. It is a map of likelihood, a statement of where the electron may be found if we ask the question. Sometimes closer, sometimes farther, never reduced to a neat miniature orbit, like a planet circling the sun. That older image, though charming, is too classical for the true softness of the atomic world. Instead, electrons inhabit shapes, patterns, standing waves of possibility. They fill regions of space in elegant forms: spheres, dumbbells, layered shells and lobes, not as tiny marbles in fixed tracks, but as distributed presences with measurable tendencies. In this sense, matter itself is less solidly located than it appears. The stable surfaces of life arise from entities whose own being is partly smeared across possibility. There is something wonderfully calming in that. Even the structures that feel most rigid are built from softness. Even solidity is, at its roots, a kind of patterned haze. Light, too, grows stranger the closer we listen. Photons, quanta of light, have no rest mass. They are massless, and yet they carry energy and momentum. They can push. This is one of those facts that sounds small when spoken plainly, and then becomes quite magical when truly imagined. Something with no rest mass can still exert pressure. Sunlight falling on an object can nudge it, ever so slightly. In the emptiness of space, where resistance is minimal, that tiny push matters. Over time, it can alter the motion of dust, influence small bodies, and even propel specially designed sails spread wide to catch the stream of solar radiation. Zoelight is not merely illumination, it is touch, a massless touch, but touch all the same, and on much smaller scales. Finely controlled beams of light can trap microscopic objects, holding and moving them with exquisite delicacy. Invisible fingers made of photons, hands of radiance. The day makes light seem obvious. The quantum world returns its mystery. Then there are neutrinos, among the quietest travelers in the cosmos. At every moment, enormous numbers of them pass through your body. They come from the sun, from distant astrophysical events, from radioactive processes, from the general restless life of the universe. They are so weakly interacting that they often pass straight through matter, almost as if matter were not there. Walls do not stop them. Mountains do not stop them. Entire planets barely count. This means that right now, as you lie listening in the dark, you are being gently crossed by a rain of nearly ghost-like particles, and you do not feel a thing. They slip through you with hardly a whisper, carrying information from the heart of stars and from violent events impossibly far away. There is something almost sacred in that image, a hidden weather of the cosmos moving through us continually, not harmful in any ordinary sense, not dramatic, not loud, just a silent passage. The universe is full of motion. The senses never report, and sleep, perhaps, is one way of becoming kind enough to imagine it. Deeper still lie quarks, the constituents of protons and neutrons, and with them the gluons that bind them. Quarks are curious because they are never found alone in ordinary conditions. Nature does not seem to permit solitary quarks wandering free for long. Pull them apart and the force between them grows, eventually producing new pairs rather than letting one isolated quark escape. It is a beautiful reversal of ordinary expectation. Many forces weaken with distance. The strong force, under the relevant conditions, effectively resists separation. Quarks remain confined, grouped together in enduring combinations. The particles called gluons carry this force, and unlike photons in electromagnetism, gluons also interact with one another. The result is a dense and lively binding structure, a self-entangling glue at the heart of matter. So within every atom's nucleus, there is not quiet stillness, but an intense hidden dance. Quarks held in close company, gluons stitching the group together, energy packed into tiny domains with astonishing strength. And yet this fierce inner life supports the soft world of paper and breath and distant traffic and moonlit rooms. Once again, the hidden and the gentle coexist. Then there is the Higgs field, one of the most elegant ideas in modern physics. To explain why certain particles have mass, physicists propose that all of space is permeated by an invisible field. As particles move through it, some interact strongly and thereby acquire mass. Others interact less or not in the same way. The Higgs boson, famously discovered in high-energy experiments, is like a ripple in that field, a brief, detectable tremor revealing the presence of a background structure, otherwise hidden. So when we ask why things weigh anything at all, the answer may involve not some little chunk of mass tucked inside matter, but a relation between particles in a field spread everywhere. Mass, then, is not only possession, it is participation. It is not merely what a thing is, it is part of how it moves through an unseen sea. This is a recurring theme in the quantum story. The deeper we go, the less isolated objects make sense on their own. Properties arise in relation to fields, to interactions, to shared structures extending across space. And that brings us naturally to quantum field theory, one of the grand languages of modern physics. In this picture, the universe is not fundamentally made of particles sitting in empty space. It is made of fields, each filling all of space: the electron field, the electromagnetic field, the quark fields, the Higgs field, and what we call particles are localized excitations in those fields, ripples or quanta, little concentrated disturbances. This is a breathtaking shift in perspective. The basic stuff of the universe is not tiny hard pellets, but continuous fields spread throughout reality. Particle is what happens when one of those fields vibrates in a particular quantized way. An electron, then, is not a miniature bead moving through emptiness so much as a stable excitation of the electron field. A photon is an excitation of the electromagnetic field. Matter and force both arise in this broad field-based view. And even when no particle is present, the field remains. So the apparent emptiness of space begins to change character. It is no longer a mere void in which things happen. It is a stage already occupied by invisible structures. Ice full of potential, a quiet sea beneath the visible waves. This leads us to one of the most haunting ideas in all of quantum theory. The vacuum is not empty. Even in a region where no particles are present, fields cannot be perfectly still. Thanks to the uncertainty principle, there is always a residual agitation, a minimal flutter, a faint, restless light. Virtual particle pairs may flicker into and out of mathematical existence. The vacuum seethes softly beneath the threshold of ordinary detection. This does not mean empty space is filled with little permanent objects hidden from us. The language here is subtle, but the central insight remains. What we call nothing is not truly featureless. Nothing. It has structure, it has activity, it leaves traces and measurable effects. One of those effects appears when two metal plates are brought extremely close together in a vacuum. Quantum theory predicts that the allowed fluctuations between the plates differ from those outside, and this difference can produce a tiny force pushing the plates together. It is a small effect, but real. Imagine that. Two objects nudged by the shape of nothingness. The vacuum, far from being a blank stage, participates. It exerts, it matters. There is another phrase for the ever-present baseline activity of fields: zero-point energy. Even when a system is cooled as far as possible, even when all ordinary motion seems gone, a residue remains. Not because someone forgot to remove it, but because the quantum world does not permit absolute stillness of the classical kind. This is both strange and oddly beautiful. At the deepest level, the universe does not fall into perfect silence. There is always a faint hum, a minimum whisper, a background breath. Perhaps this is one reason the image of the vacuum feels so restful at night. It is not dead emptiness. It is living quiet. It is not blank absence. It is subtle presence. It is the dark room of the cosmos, never fully empty, never fully still, but calm in a deeper way than noise. Some have wondered whether the energy of empty space might be related to dark energy, the mysterious cause of the accelerating expansion of the universe. The details remain unsettled, and theory and observation do not yet sit together as peacefully as one would like. But the possibility remains tantalizing, that the large-scale fate of the cosmos may somehow be tied to the hidden restlessness of the vacuum itself. If so, then the most enormous motions in existence may be linked to the softest fluctuations of nothing, the universe stretching, because emptiness is not empty. That is such a midnight thought that it almost feels composed for this hour. At this point, let us pause again. Notice how far the journey has carried us without once asking us to grip too tightly. We have moved from electrons to photons, from neutrinos to quarks, from mass to fields, from particles to vacuum, from empty space to the expansion of the cosmos. And yet the rhythm need not quicken. None of this requires urgency. The hidden world is in no hurry. So breathe slowly. Let the shoulders loosen. Let the bed carry more of your weight. The same invisible fields that underlie stars and atoms also underlie your body now. The same restless vacuum that flickers between galaxies also lies between the molecules of the room. The universe is not elsewhere. It is here, quietly being itself beneath the stillness of the night. And from that stillness, we can drift into another region of the story, where quantum ideas begin to become tools. The most famous of these is the quantum computer. A classical computer stores information in bits, each one either 0 or 1. A quantum computer uses quantum bits, or qubits, which can exist in superpositions of 0 and 1 before measurement. This allows certain calculations to be arranged in ways that explore many possibilities together, using interference to amplify useful outcomes and cancel others. This does not mean a quantum computer literally tries every answer in a simple brute force way. Truth is subtler and more delicate. Its power comes from shaping the landscape of possibilities, so that the desired result emerges with increased likelihood when measured. In the right problems, this can offer extraordinary speedups. Some algorithms can factor large numbers far more efficiently than known classical methods. Others can search more cleverly through vast spaces of possibility. Still others promise advantages in simulating molecules, materials, and quantum systems themselves. But quantum computing is difficult because quantum states are fragile. Noise, heat, and unwanted interactions can destroy the delicate superpositions and entanglements that make the computation valuable. Building stable, error-corrected quantum machines is one of the great technical challenges of our time. There is something very human in this. We glimpse a new kind of power and immediately meet the tenderness required to hold it. Quantum information is not like a stone tool you can simply grip harder. It is more like frost on glass. Too much disturbance, and the pattern vanishes. And perhaps that is why the field has such a quietly romantic quality. It is a technology of delicacy. Closely related is quantum cryptography, where the laws of physics themselves help guard secrecy. In certain protocols, information about a key is encoded in quantum states of light. If an eavesdropper tries to intercept and measure those states, the disturbance introduced by measurement reveals the intrusion. So security becomes less a matter of hoping a mathematical puzzle remains hard, and more a matter of trusting the deep behavior of reality. Secrets protected by the structure of the world, whispers kept safe, because to overhear them is to alter them. There is a certain nighttime poetry in that. Then there are quantum sensors, devices that use superposition, interference, or other quantum effects to detect incredibly small changes, variations in magnetic fields, tiny shifts in gravity, minute accelerations, exceptionally precise measures of time. The quantum world, so often associated with uncertainty, also offers forms of precision beyond classical reach when handled gently enough. Atomic clocks are a beautiful example. They use the natural oscillations of atoms as reference rhythms, and in their most refined forms, they keep time with such accuracy that they would barely drift over spans almost too large to contemplate. Time, measured by atoms, held in exquisite calm, becomes a kind of music of astonishing steadiness. And because gravity affects time, clocks of such precision can even sense differences in height. A clock slightly higher in a gravitational field ticks differently from one slightly lower. So time itself, once thought universal and uniform, becomes textured by relativity and revealed by quantum measurement. The deeper physics grows, the more it begins to resemble art. Another striking quantum phenomenon appears in superconductors. In ordinary conductors, electrical current encounters resistance and loses energy as heat. But in certain materials cooled sufficiently, electrons form paired states and move in a coordinated quantum way that allows current to flow without resistance. No loss, no waste, a perfect slide through matter. Superconductivity reveals that under the right conditions, large numbers of particles can settle into coherent collective behavior, acting not as scattered individuals, but as one organized quantum state. It is a glimpse of order born from cold and quiet. Superfluids offer another version of this beauty. Certain fluids, when cooled to extremely low temperatures, can flow without viscosity, slipping through tiny channels, climbing surfaces, circulating endlessly in loops with no apparent slowdown. The liquid behaves almost like a single giant wave, coordinated and uncanny. This is quantum mechanics made visible, not only hidden in atoms or mathematics, but spilling upward into the macroscopic world where we can see its grace. The fact that such states exist is reassuring in a peculiar way. It means the quantum world is not completely confined beneath the threshold of human experience. Under special conditions, it blooms into visibility. The hidden music becomes audible. From technology and collective quantum states, the mind can drift back toward interpretation, toward the question we quietly set aside earlier. What does quantum mechanics mean? There is the well-known Copenhagen style of thinking, where quantum system is described by a wave of possibilities until measurement yields a definite result. This is often taught because it works well in practice. It tells us how to calculate and how to interpret laboratory outcomes. Yet, it leaves some of the deepest metaphysical questions suspended. Then, there is the many worlds view. Instead, all possible outcomes continue, branching into distinct histories. The world splits, or rather reality unfolds into multiple consistent versions, and we find ourselves in one branch. This idea can sound extravagant, but it carries a strange calm with it. No special collapse, no abrupt magic, only continuous evolution and branching experience. There is also pilot wave theory, where particles possess definite positions guided by an underlying wave. This restores a kind of determinism at the price of a more non-local picture. Other approaches propose spontaneous collapse, where superpositions end by themselves under the right conditions. Still, others emphasize decoherence, the process by which interaction with the environment rapidly suppresses the visible effects of superposition in large systems. Decoherence is especially helpful for understanding why the everyday world looks so classical. Macroscopic objects are constantly interacting with countless surroundings. Air molecules, photons, vibrations, thermal noise. These interactions leak away the delicate phase relationships that sustain coherent superposition. The larger the system, the faster this usually happens. And so tables become tables, chairs remain chairs, and cats do not appear suspended in visible mixtures of life and death. The world of daily life is in this sense what the quantum world looks like after tremendous entanglement with its environment has washed away the obvious traces of strangeness. Reality falls asleep into classicality. I like that image. The ordinary world as the dreamless surface produced when deeper quantum possibilities are constantly touched by everything around them. The bed solid beneath you, the wall stable, the room holding its shape, all of it emerging from hidden layers that, left on their own, would be far less definite. But beneath that settled surface, the old softness remains. Then comes quantum tunneling, another of those ideas that sound impossible only because our classical intuitions are too narrow. In ordinary thinking, if a particle lacks the energy to cross a barrier, it cannot get through. End of story. Yet a quantum particle is described by a wave function extending into space. If a barrier is narrow enough, there can be a non-zero probability of finding the particle on the other side without its ever having classically climbed over. It tunnels through. This is not metaphor. It is real and measurable. It powers devices. It influences chemical processes. It sets limits on tiny electronics. And in the stars, it helps make fusion possible. Without tunneling, the sun would struggle to ignite the reactions that produce its light and warmth. So the daylight on your skin, the growth of leaves, the weather of the planet, the warmth of morning after cold night, all owe something to particles slipping through what should have been forbidden. The impossible, very quietly, is what lights the sky. There are even hints that biology has found ways to use quantum effects. In photosynthesis, some evidence suggests that energy may explore multiple pathways in an organized way that helps living systems harvest sunlight efficiently. Certain proposals about bird navigation involve quantum-sensitive molecules responding to Earth's magnetic field. There are ideas, still debated, that smell itself may involve tiny quantum processes. Nature, it seems, may have been employing subtle quantum tricks long before humans named them. Life is older than explanation. The universe was doing this before textbooks, before laboratories, before language. And then, if the mind is still wandering with us, we can drift farther outward, to the earliest moments of the cosmos. In the beginning, when the universe was incomprehensibly small, hot and dense, quantum fluctuations would have rippled through everything. Tiny variations in energy and density, born from the uncertainty and restlessness of fields, would later be stretched as the universe expanded. Those minute irregularities became the seeds of structure. Over immense spans of time, gravity amplified them. Matter gathered, stars formed, galaxies took shape, so the large-scale architecture of the cosmos may trace it back, in part, to tiny quantum fluctuations in the early universe. The galaxies are magnified whispers. The clusters of stars are ancient ripples, grown immense. Every grand spiral and every glowing swarm in the night sky may carry, hidden in its ancestry, a tremor from the smallest scales. This is one of the loveliest reversals in all of science. The biggest structures in existence may owe their origins to microscopic uncertainty, the vast born from the minute, the visible cosmos from invisible tremors. And there, near the boundary where quantum theory meets gravity, another great mystery waits. Pulse. These objects are often imagined as the ultimate triumph of gravity, regions where space-time curves so deeply that not even light escapes once it passes the event horizon. Yet quantum theory will not remain silent there. Near the horizon, quantum effects matter. Stephen Hawking showed that black holes, when quantum fields are considered, should emit a faint thermal radiation. Very slowly, over unimaginable times, they can lose mass. So even black holes are not fully black. Even the most absolute darkness leaks. The meeting of gravity and quantum theory in such places remains incomplete. We do not yet possess a fully successful quantum theory of gravity accepted by all. But the pressure of the problem is immense. At singularities, in the first moments of the universe, in black hole interiors or horizons, the old theories strain against one another, asking for deeper unification. Some proposals suggest spacetime itself may come in discrete units at the smallest scale. Others imagine new symmetries, vibrating strings, loops, holographic descriptions, or relationships between geometry and information. Some even connect wormholes and entanglement in provocative ways, hinting that two distant regions of space might be linked in deeper descriptions by the same sort of correlations we met earlier. Whether these ideas prove fully true or evolve into something else, they point again toward a remarkable possibility, that space, time, matter, energy, and information are not separate kingdoms, but aspects of a single deeper order we have only begun to glimpse. And now, at the far edge of our journey, there is one more thought to rest within. What if the universe is not, at bottom, a collection of disconnected pieces at all? What if separateness is partly a large-scale convenience, a useful appearance, while the deeper reality is more unified, more relational, more whole than it seems? Quantum theory does not force one simple mystical conclusion. It is science, careful and demanding, but it does encourage humility about the boundaries we casually draw. This particle and that one, here and there, empty and full, cause and effect, observer and observed. The more closely we look, the more those neat divisions blur. Entanglement binds systems into shared states. Fields extend everywhere. Vacuum is structured. Measurement is interaction. Geometry may emerge from relation. The cosmos grows from fluctuations. And so the universe begins to resemble not a pile of detached objects, but a single vast process, richly patterned, internally linked, softly indivisible, in ways our everyday language only partly captures. This is not a conclusion to seize too hard. It is more like a final room in the museum, lit only enough to suggest its shape. A room of connectedness, a room in which the hidden world beneath sleep feels less mechanical than musical. A room in which existence itself seems woven. And perhaps that is a good place to rest, not with mastery, not with a perfectly closed explanation, but with a feeling that reality is stranger than fear and gentler than certainty, that beneath the solid day lies a softer architecture, that the emptiness between things is not empty, that the distances we trust may conceal invisible threads, that light touches without weight, that particles wander as possibilities, that your body, your breath, your sleeping mind are already part of this deeper order, held within it, made of it, carried by it every night without effort. So let the need to understand continue to loosen. Let the words become slower now. Let the images spread and thin. Imagine the electron cloud dimming into mist. Imagine the fields settling into a low, invisible hum. Imagine the virtual flicker of the vacuum, like soft static in a darkened room. Imagine neutrinos passing soundlessly through the house, the city, the planet, the sleeping world. Imagine the stars above, shining because tiny nuclei once tunneled through barriers they should not have crossed. Imagine distant galaxies still carrying the memory of ancient quantum ripples from the beginning of time. Imagine space itself, perhaps, held together by relations too delicate for ordinary sight. And then imagine none of it too clearly. Let it all blur. Let it become atmosphere. Let it become the kind of thought that no longer asks to be solved. The universe does not need to finish itself for you tonight. It can remain open. It can remain wide. It can remain strange. You can drift without closing the circle. You can fall asleep inside the question. Perhaps somewhere beneath waking thought, the mind already understands how to live with mystery. Perhaps sleep itself is a kind of agreement with the unfinished nature of things, a nightly surrender to what cannot be tightly held, a soft acceptance that not everything must arrive as one fixed bright answer. Quantum physics, for all its difficulty, teaches something similar in its own language. The world is not always one crisp story told in advance. It is layered. It is probabilistic. It is relational. It is full of hidden motion in apparent stillness, hidden structure in apparent emptiness, hidden unity beneath apparent separation. And so are we, perhaps. We too are layered beings, waking and dreaming, conscious and drifting. Precise for a while, then soft around the edges, we too move between the definite and the not yet decided. We too are made of hidden processes carrying us without permission and without complaint through each day and every night. So the more the script of thought begins to dim, the more fitting this subject becomes, because the quantum world is not a thing to conquer. It is a thing to enter gently, and now we are already at the threshold of silence. The room is quieter than before. The body may be heavier than before. The words need less of you than before. So let us remain here a little longer, in the almost dark. The hidden world below sight, the soft staircase of energy, the wave that arrives as a point, the question that changes what it touches, the uncertainty folded into nature, the cloud of possibilities before one result, the linked particles across distance, the vacuum that hums with invisible life, the fields beneath matter, the stars lit by tunneling, the galaxies seeded by fluctuations, the universe, perhaps, woven more tightly than it appears, and you, resting within it, safe within it, already held by laws older than language, by structures deeper than thought, by a cosmos that has been carrying complexity in perfect silence for billions of years. Nothing more is needed now. No summary. No final lesson. No hard conclusion tied neatly with a ribbon. Only the slow release. Only the dark. Only the sense that reality goes on, wide and deep, and quietly unresolved, while you drift away from the effort of following it. So let the images fade. Let the particles dissolve into haze. Let the fields become only background. Let the background become silence. And if one thought remains, let it be a small and peaceful one, that the world is stranger than it seems, and softer too, and that tonight you do not need to hold any of it. You may simply rest inside the mystery, and let sleep do the rest.